Hi everyone, Martin here. Welcome to the Inner Loop. In this episode I wanted to talk a bit about hidden algorithms. It's all inspired really by a visit to the Tangmere RAF base. It's actually now a museum. Tangmere is on the south coast near Chichester in the UK, and it was actually a base for fighter aircraft during World War II. So there was Hawker Hurricanes and Spitfires there, and they were used to defend the UK during the Battle of Britain and sort of during the war. There's a museum there now, and what really captured my interest there was what's called the Mark 16 bomber site. There's a little sort of description of the Lancaster bomber and how they used to bomb them up and send them on their way. But actually solving the problem of dropping a bomb on somewhere, it's actually quite hard. Mathematically it's quite tricky because you have to consider a number of things. You have to consider the speed at which you're flying. You have to consider the speed of the wind, and you have to consider the speed that the bomb will actually drop. Bombs do strange things because they kind of get up to speed and then they reach some kind of terminal velocity and then they land. There's a lot of maths involved in that. To calculate that in a static way, to say, right, I'm just going to fly to a point which I can calculate and then drop the bomb, that'll be fine, means that the bomber is actually a sitting duck whilst it's kind of coming to its point. Whereas if you can actually fly the aeroplane around and then drop your bomb, you're much less vulnerable. But in order to do that, you've got to actually calculate the time to let the bomb go much more accurately, and you need a computer for that. So we're talking 1941. So when you think about a computer, you think about something with microelectronics inside that runs at gigahertz and does a huge amount of maths. I've put a picture of the bomb site and a link to it. You can go and read about it if you're interested in such things. But this thing was a mechanical computer. It had like gears and cogs and stuff. But those gears and cogs and stuff were designed to do all the differential and that, calculus and all the other bits and bobs that were needed in order to calculate from the position of the aircraft when to let the bombs go, and gave the bomber a sight. I know this is all a bit gruesome, but in some ways I find the actual history of the computing absolutely fascinating. So that's the world of analog computers done with cogs and wheels, and I guess it's the origin of when we say, oh, I'm just going to dial in something, I'm going to, put those numbers in, let's dial in a few numbers. This is all about the original kind of turning knobs and dialing numbers in. There's another great video I'll put below, which is the renovation of an IBM Cheese slicer. IBM make computers, right? But have a look at the cheese slicer. You'll be absolutely amazed that this is a business machine made by IBM. Have a watch of the video anyway. But there's the algorithms hidden in so many things, and I wanted to look at some of the videos that I've been making over time. Everything I've done is kind of flat, it's kind of two-dimensional. So what I wanted to do now is to up the game and see if I can make things three-dimensional. So there's plenty of 3D libraries for doing that. But this is the Inner Loop, this is algorithms. So I wanted to look at the algorithm that turns a 3D shape into a 2D picture. It's something that graphics cards do when you play World of Warcraft or Portal or whatever it is you play. You take it for granted that this 3D world is in front of you. But I wanted to look at the mathematics, at the linear algebra, what goes on underneath. What's that graphics card doing when it creates a picture? I guess the only way to unravel this is put the camera down and let's draw a picture and look at what the graphics card is doing. I drew that. It's all about how robots these days dangle things and we sort of jump around to buy them. Okay, so what's the problem we're actually trying to solve? Imagine we have a point in space here. Let's give it a name, x1, y1, z1. So here's some kind of axis.
Z, X, big X, Y. Okay. Here's our point in space. But I want to see that point in space on a screen. Now my screen is flat. So where is my screen? So let's put a screen here. So that's the screen, that's my monitor. But where am I looking from? Well, I'm actually looking from a point perpendicular to the screen here. We'll call that X2, Y2, Z2. Still haven't solved the problem, because what I want to know is if this is a 2D screen, this has an X coordinate and a Y coordinate. This line is going to hit this screen somewhere in the X and Y coordinate based on the coordinate system of my computer screen. These points can be anywhere in space. So how do I render this point from this point to here? How do I find out what that point is? Let's give that a name. That point there is called X3, Y3, Z3. Or in terms of this screen here, it's something like big A X by, say, big B Y in this coordinate system. So the challenge is to calculate A and B based on X2, Y2, Z2, which is where your eye is, and X1, Y1, Z1, which is the point you're looking at. And that's how we can convert from 3 dimensions to 2 dimensions. Well, first thing I did to look at this problem was think about how do you specify this point? Because it's actually quite difficult to envisage that point. How do you actually envisage that point? For us humans, it's much easier if you think about your camera, which has got a lens on it. It's not a very good camera. You've got a camera, shutter button here. I don't know, thing on the back, camera strap. We tend to keep our camera horizontal. And then we have if you think about a tripod that this thing might be attached to, we tend then to think about 2 things, which is our position, where's the camera located, and then we need to think about, so that's the X, Y, Z position. Then we need to think about the pan, which I guess is this angle here, pan. Pan angle. And then the other thing we do with our camera on a tripod is we sort of tilt it. So you tilt your camera with that doodly. All cameras have that, all tripods have that doodly, don't they? It comes off here. And that's what you use to pan and tilt the camera. So, what I wanted to solve was X, Y, Z, X2, Y2, Z2. The point on my whatever I'm making, some point, which is my 3D object, pan and tilt, and get out an answer for A and B. Because then I can render A and B based on these things that I know. Pan and tilt. The last thing you've got on your camera that we also need to worry about, if you think about it when you're filming someone, is the zoom. Now, the way that zoom works mathematically, well, I've worked it, is L here. There's a length L, which is the distance from the screen. So I can base the screen anywhere I like. The closer the screen is to the object, the less zoomed in you actually are, or the more zoomed in you are. The further back you go, the more angle you gain, the more angle you have through the thing, and the more you zoom out. So this length L, the longer it is, the closer you get to the object, and the more zoomed in you become. So it's actually the wrong way around. So the algorithm that I was looking at then is, let's write it down. How do we get from some sort of transformation, some T, transform. So we're going to transform from x2, y2, z2, L, and x1, y1, z1, pan, tilt, and that transform is going to take us to, it's going to give us two numbers, A and B, and then A and B tells me where to plot my point on my 2D monitor. Can't be that hard, can it? So that is the basic algorithm, much as the twisting the knobs or dialing in anything else. That's the basic algorithm that I wanted to solve. So let's have a look about how the sort of mathematics that goes into trying to solve that.
Okay, so what we're trying to find is the value of this point here, and this we called x3, y3, z3. This is what we want to find out in this step. What do we know? We know this point. We called that x2, y2, z2, and we know this point. This is the point in the world that we actually want to look at. We call that x1, y1, z1. This point here is the point where our camera meets normal, where our line is a normal to the plane, where we literally look straight at the plane. This point we're going to call xn, yn, zn. This point here, the one that we're going to trying to find, is x3, y3, z3. This point, if we can work this point out, this is clearly going to be useful to us. And a bit of simple geometry based on the pan and tilt will actually give us this point. So let's work out the value of that based on the pan, tilt, this and that and that. We can work that out based on all the things that we know. My assumption in terms of pan and tilt is that, let's use a different colour, it's black. This is the z-axis, straight up. This is the x-axis, sort of along. And this is the y-axis. It doesn't really matter which way they point, but they've all got to point the same way. So, in terms of pan and tilt and doing the geometry to work this point out, what I'm saying is that if we have no pan and we have no tilt, then we are looking directly along the x-axis. This is pan. So as we pan, we go towards the y-axis, and as we tilt, positively we go up towards the x-axis, towards the z-axis. So the tilt angle is in here. If that makes sense. So tilt takes us, as the tilt angle increases, we go towards z. As the pan angle increases, we go from x to y. So based on that, we can work out, using pan and tilt, we can work out a value for x n, y and z n. So let's do this algebra in red. So xn equals x2. Also, we're going to start here, and we need to know how much x is a proportion of L. And actually, if this pan angle is 0, then it's all of it. If this pan angle is 90 degrees, then it's y. So it's going to be plus cos, and let's call it P for pan. But it's going to be a proportion of L. So we'll put a times L. And also we know that as we tilt the thing up, the amount of that value there actually, as we tilt it up, actually this will decrease. So that is also a function of cos of the tilt. T for tilt. So yn equals y2 plus sine the pan times L times cos tilt. And the final one, z, equals z2 plus, and now this actually doesn't, if you think about pan and tilt, if we're pointing straight up, then the only value z actually doesn't change at all. Z takes the full height, takes the full value of L. So that actually is L times by sine of the tilt. And the pan makes no difference to z. If you twist around here, this height doesn't change. There's clearly a third angle that we could have used, which is actually to tilt the, if you think about this frame, to tilt it round like that. So it's almost like if you turn your head upside down. But it's rare that we actually sort of tilt our heads. We might change from landscape to portrait, but this is enough maths already. We're here. Now we've found this point. So how do we find this point? Let's do this line here in purple on the other side. We know that this point lies, well, if we're going to display it on the screen, this point lies somewhere between here and here. So that's actually very easy to to write down mathematically. It's quite simply x3 equals, again, x2 plus, and now we're going to come up with some scalar, some number t. I've used t already. Let's call it s. S. So some value s, which goes somewhere between here and here. So this is, we're making up an equation for this line. It's s times by the difference between x1 and x2. So if s is 1, we want it to be there. if s is 0, won't it be here? So let's do s times x1 minus x2. So you can see here this scalar number, s, takes us from here, x2, and when s becomes 1, this x2 becomes 1, that cancels out, and x3 becomes x1. So actually, we've done something quite handy here. If we can bound this value between 0 and 1, we know that we're actually on the screen. We could put the screen behind the viewpoint. That would be fine. Mathematically, that's fine. But actually, logically, it doesn't make any sense because you can't see it. You can't see, your eye's here, the screen's behind you. We can't see anything. Okay, so the same applies for y3. y3 equals y2 plus s y1 minus y2. And the last one, z3, z2 plus s z1 minus z2. So this is starting to look quite promising now. We've got this point, we've got this point, but unfortunately we've got this s, which we don't really want. So how do we get rid of s? Well, there's one other thing that we know, which is actually really handy. And that's the property of vectors. So a vector is like a line. It's a line, points in a particular direction, but it doesn't actually describe a line. It just describes a direction. So although this line has a start and an end point, the vector value of this is actually just represents the x, y, and z proportions of how far you'd go in any one particular direction. So this vector could be anywhere in space, but it always points that way. If you change the values of x, y, and z, then it could point somewhere else, but it could still be anywhere in space. But one really handy feature of vectors is that if they're perpendicular and you take their dot product, which is a multiplication of their values, it's always equal to 0. So we know this vector here. It's called the normal. We know the normal vector here because it's actually this line here which we've already described. So, and we can describe this line also as a vector. And in creating their dot product, it gives us the equation of this plane, and therefore we've got an equation that will help us solve for s. So let's write that out, and then you can see the three parts here which will come together to solve the first part of the problem, which is how do we find x3, y3, z3. So let's label these vectors. This is 1, this is 2. So what's the equation for vector 1? Well, it's actually here. So the direction in which x points, you'll see it actually points in the opposite direction to the x-axis, to the way that this is pointing. But direction of this is just cos p times cos t. So vectors tend to get put in brackets like that. And why? Well, again, the y vector again points in the opposite direction to this line. So that would be minus sine p times cos t. And funnily enough, the z vector, sine t. Right, that's not useful to us yet, because we know that in order to be on this plane, this dot product of 1 and 2 is equal to 0. So what's the 2 vector? Number 2. Well, we've just actually got the number 2 vector here, because we've got this point, and this is our unknown. So now we can express this vector in terms of this. So this vector here is actually very simple. It's actually x3 minus xn, y3 minus yn, z3 minus zn. Dot those two together, and we know that that equals 0. Has that helped us? Yes, because this here is this. This here, which we're after, we have here. And so this will allow us to find a value for s. I don't actually propose to do all that simultaneous equations, to go through that, because it's actually quite torturous. I think I might have my original you can see I really struggled to simplify this, but it does simplify, and it simplifies down into some quite simple terms, something like this, sort of y2 sp blah 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 blah. Okay. Okay, the final phase. So we want to convert from this point into an xy. We want to convert into an xy coordinate on our frame. So the final phase now is to try and calculate these values of x and y in this frame of reference, on this frame, which can be pointing if you think about it in any direction. This is our original frame of reference, x, y, z. And down here I've actually written out the equation that actually solves this problem, and I'll just talk you quickly through it. If you think about this frame, it because we're like a camera, we're never actually turning the camera through any angle. It's only panning and tilting. So the value of x, this value of x, is only ever going to depend on the x and y values. The z value is never going to affect how far along the frame you go. So x is actually equal to x3 cos p, cos the pan. So if you're not panning, you're looking straight along the x-axis. So the value of x is actually the value of x. Plus y3 sine p. So if you're pointing this way, if you're panned 90 degrees, then it'll all be y. So if we turn that round there, the value of x will actually be the y value. The y value in this reference, frame of reference, well, that's actually takes on the opposite value, opposite version of this. So if you imagine this was flat, it was completely tilted straight down, then y would actually be equal to y, and x would be equal to x. So that's exactly what we get here. Y will now be x, you see here, this pan version will come up here, and y will come out here. But if you tilt it, as you start tilting upwards, that's when it's completely flat, when the tilt is fully up. If it's not tilted, then y actually is parallel to z. So what we add on here is z3 times cos t, cos the tilt. So 0 tilt y equals z. If it's 90 degrees, then it's sine t. So this will give us this here. Y will become y3. So bit of logic really. I mean, I guess there could be some vector algebra that actually does this formally, and if there's any mathematicians who want to comment on this. This is essentially a change of it's a change of reference, isn't it? It's, you know, this is the original coordinate system, this is the new coordinate system, and this seems to translate it. I started writing down a z value, but there isn't a z value because it's 2 dimensions now. So now we've gone via this mathematics, we've gone from 3 dimensions to 2 dimensions. I propose now that we have a quick look at the code. So here it is. This is the function called AllOne. It takes in a coordinate, pair of coordinates, which is the point in the world. It returns out, which is going to be 2 coordinates, which is the point on the screen. It takes in 3 values for the viewpoint, and it takes in cos of the pan, sine of the pan, cos of the tilt, sine of the tilt, and that value L. L is the distance from the screen. So they are. See, you see all the values that we had. You'll see that I haven't done the mathematics for cos sine, cos pan, sine pan, cos tilt, and sine tilt within this function, because they're actually, those trigonometric functions are actually quite expensive on the CPU. So it's easier to calculate them elsewhere, and then if you're doing a million points, that value is already available to you. So there's another little function just above here actually called matrix, which actually calculates those things. Okay, so it takes in those values, and here is this the value s that we were talking about. This is that that value which tells us whether we're on the screen or not. It's also had a bit of because there's been some simplification to a lot of this. You can see that actually it has to be checked between 0 and L here. If it is less than 0 or greater than L, then this returns 0 and kicks out, so we're not even on the screen. Here is the calculation of the, what I think we call them x3, y3, z3. Again, it's all in terms of this s value. And then here's that final step where we take the x, y and z values and then we convert them into just x and y, which is the out values. There's the z. And final thing here is a little range check, just to say, oh, you know, are we actually within the screen? So we have an actual screen size of x sides, y sides. Here you'll see I also added the half the screen. So the centre of the screen actually, any values that go negative go like half my screen size will actually be on the screen. So the centre of my screen is here, but mathematically it's actually in the top left hand corner. And that's it. That is all that mathematics that we were looking at, kind of boiled down into really that. So that's the hidden algorithm. That is the algorithm that that we see on graphics cards. That's the algorithm which is burnt into graphics cards. That's hidden, much as the bomb aiming device or anything else. This is what graphics cards do all day. They do this kind of mathematics. Final things we need to consider before we can actually draw something on the screen. Look here. Here's the inner loop of drawing the biots, drawing the sort of flying birds, which you're going to see. You see, first thing we do is call this matrix function. That's to calculate our sines and coses and all the rest of it. Then we measure the flock. So this actually calls that three-way function. But the next thing we need to do, which I haven't really talked about very much, is you actually need to sort the points into the right order. You're not going to generate a realistic looking thing if you plot the things that are closest to you last. You've got to plot everything in the right order. So although my function, which we just looked at, does clever stuff, there's other stuff that graphics cards need to do before they actually deliver the final image to the screen, which is to make sure that you draw things in the right order, back to front. And that's what this does here, sort flock. Then we can actually, here's our thing here, AllOne. So here now we can actually do that bit of mathematics in terms of 3D to 2D. We can do that there, and then we draw our biodes on the screen. Right, so what follows on the end of this video now is just some examples using these transforms. There's some flying birds. You can watch them fly about. There's like an exploding jar. The music for this was actually provided by Patrick Bartness. I often talk about Patrick because he's often contributing music and ideas and various bits and bobs to this channel. Patrick's kind of nailed the music that you need to go with an exploding virtual 3D jar. So please enjoy that. Please enjoy the other animations. Thank you very much for watching, and I'll see you next time on the In a Loop.
you.